Hello, welcome to our lesson on logarithms and log functions. So what exactly is a logarithm? So a logarithm, which is just abbreviated log, L-O-G, it really just represents a power or an exponent. So sometimes people are a little bit hesitant to work with these, or they have these negative emotions tied to logarithms. I'm not really sure why. Maybe just your first experience with them wasn't the greatest, but they are honestly just exponents. So if you can handle exponents, you can handle logarithms. For example, when we are looking at this expression here, this log expression, we would read it as the log base 4 of 16. So we're going to interject two words into that expression. So it's log base 4 of 16, where again the 4 represents the base of the log, and the 16 represents the argument of the log. So 4 is the base, and we call 16 the argument. Okay, so log base 4 of 16 is how we read it. Now what it's asking is for the exponent that connects that same base with the argument 16. So the question, when you're reading log base 4 of 16, what you're asking yourself is, what is the power of 4? What is the exponent of 4 that would produce 16? So again, we're just looking for a power or an exponent, which means in this case our log expression is equal to 2, because the log base 4 of 16 is going to be equal to 2 because 2 is the power of 4 that produces the 16. So here I'll say because, again, 4 squared is going to make us 16. If I raise 4 to the power of 2, I would get that argument of 16, okay? So it's just a power, it's just an exponent. It is the power that connects the base of the log to the argument. So we're going to practice just evaluating a few, and these are all things that should be doable without the calculator. For example, number 1, log base 8 of 64 is asking 8 to what power makes 64? We know that that's the second power, and so that expression is equal to 2. Or the log base 8 of 1 over 64. If I want the 64 to go to the other side of the fraction, then negative 2 would be my exponent connecting that base with that argument. Or 7 to what power makes 343? That's the question when we read log base 7 of 343. That's going to be 7 to the third power. So the value of that log expression is going to be 3. Now if you look at number 4, the log of 1,000, there isn't a base written. So sort of like when we don't see, if we have an x, we don't always write the 1 that's in front of the x. We also don't write the 1 that we have for the exponent there. There's just an implied 1. There is an implied base here, just not a 1, because 1 raised to any power would be 1. The implied base here is a 10. So even though we don't see it, this is the same thing as the log base 10 of 1,000, so it is asking 10 to what power makes 1,000. That's going to be the third power, so that expression is going to be equal to 3. So when the base of the log isn't shown, it's a 10. Okay, same thing here. So even though we don't see it, this is the log base 10 of 1/100th. So this is asking 10 to what power makes 1 over 100. Well, I know 10 to the second power makes 100, so 10 to the negative second power would make 1 over 100. Next one we have the log base 7 of 1. 7 to what power is going to make 1? Has to be 0, because anything raised to the power of 0 is going to be 1. So in fact, regardless of what the base is here, if the argument is a 1, the value of that log expression has to be equal to 0, because again, anything raised to the power of 0 is 1. So if the argument of the log is 1, then the value or the power that the value of the expression or the power has to be 0. Okay, and then here we're looking for the log base 2 of 0. So this is asking 2 to what power is going to be equal to 0. So if I'm trying to figure out 2 to some power to make 0, it's not going to be possible. And you can think about our exponential function, 2 to the x power, because this exponent we're looking for is unknown, right? If I graph 2 to the x power, we saw this in our previous topic, that this is what the graph basically looks like, where we have an asymptote here, right? It's not going to be possible for us to make or to raise 2 to a power and make it equal to 0. It's going to approach 0. The smaller the exponent I pick, as x approaches negative infinity, our function will approach 0, but it can't get there. So there is no power of 2, or any base that is going to make a log expression equal to 0. So we would say that this is undefined. Okay, and then the same thing is going to happen here. If I'm looking for 5 to some power to be equal to a negative 25, again, I'm looking for, or if I look at 5 to the x power, just like 2 to the x, basic same picture here, not only are we not going to be able to get to 0, but we're not going to go below 0. So this isn't going to be possible. It's not going to be possible to raise 5 to a power to make it negative. As small as I make my exponent, the values just keep approaching 0, but they can't get to 0. They also can't become negative. So this again is going to be undefined. And so we'll generalize here. If we're trying to evaluate a log expression, a 0 in the argument and a negative in the argument, not going to be possible. That would leave us with something undefined. So we cannot evaluate logs of negative numbers or 0. Those expressions would be undefined. Okay, so those are what we call the common log. We also have a natural logarithm. So the natural logarithm is abbreviated ln. Not really sure why. I think this has something to do with the French language, but ln represents our natural logarithm. The common log, we can put really whatever base we want, and we can put, I'm ahead of myself. Okay, I can put whatever base I want for the common log. For the natural log, our base is always e. And in fact, I can make, this is what I was going to say, the common log have a base of e, but with the natural log, that is it. So when you're seeing the natural log, you're going to see something like this. We would read that the natural log of 1. So again, we're going to interject that word in there. So natural log of 1, and we don't see a base written, unlike with the common log where there's an implied base of 10 if we don't see it written, or we can make the base whatever the number we wanted. This will always be a base of e. So this is the same as the natural log with a base of e of 1. Okay, so we don't see the e, but the base of e is there. Again, e is the base. 1 we would call the argument of that log. So again, we're just looking for a power. In this case, it's asking what is the power of our base of e that's going to make a 1. So again, it's a power that's going to connect the base here with the argument that's here. So e to what power makes 1? That's the question. Well, we just said that anything to the power of 0 is going to make 1. Therefore, the natural log of 1 is going to be equal to 0. Again, this is because anything raised to the power of 0 is 1, because e to the 0 power is 1. That is the power, that is the exponent that connects that base with that argument. Okay, so let's practice just evaluating a few more. If I asked you for the natural log of e, remember there's this invisible base e here. So the question here is e, that invisible base, raised to what power is going to make the argument, which is also an e? Well, if I want to raise something to the first power, it's the only way I get back to that something. And so this is going to be equal to 1. If our base and our argument are equal, this is going to have to end up being a 1. Hopefully that makes sense. Okay, kind of a similar concept here. This is asking e to what power is going to make e to the second power. So we have this base of e, and I want to know the power that connects that base with this argument. So in other words, e to what power makes the argument e to the second power? Well, that power has to be 2. So this one is going to be 2. And what we saw in these last two problems is when that base, excuse me, and the base there and the base here, when these are equal, they're basically going to undo one another and leave us with the exponent. Here the exponent is explicitly written as a 2. Here the exponent is a 1. Okay, so we end up here with the value of 2. And then here, natural log of 0, just like common log, it's not going to be possible. This is saying what power of e is going to get us to an argument of 0. Can't happen. So we looked at e to the x, just like 2 to the x, 5 to the x, same basic exponential growth picture. Cannot get to 0, and definitely cannot get to anything below 0. So these last two are going to be undefined. Again, I can't take the log or natural log, any kind of logarithm. So this one looks different. The natural log, though, and the common log have the same properties, just different bases. Okay, so this is still going to be undefined. and as well here, undefined. Okay, so natural logarithm looks different than the common logarithm, but that's it. It looks different, has a base of e, but acts the same way, has all of the same properties. Now, I don't want us to be doing a bunch of calculator work here, but of course there are logarithms that don't have exact values. For instance, if we jump down here to the log of 50, remember there's an implied base of 10 there. So if I'm trying to evaluate the log of 50, I'm looking for what power of 10 is going to make 50. Now there's not obviously an exact power of 10 that makes 50, so the only way to get an approximation for this, well, not the only way, but the easiest way to get a really precise approximation for this is to use the calculator. But we could ballpark this without the calculator, because in this case, for example, I know 10 to the first is 10, and I know that 10 squared is going to be 100, and because 50 is right in between 10 and 100, I know that the exponent I'm looking for here has to be between 1 and 2. So some decimal amount between 1 and 2 is actually probably good enough information for me to understand once we get into some context and we're solving, to understand what my solution is going to be like. But again, the only way to get a really close approximation is to use calculator. So the Desmos calculator that I'm going to show you actually has 3 logarithm buttons. It has, we're going to go to our functions menu in Desmos, and we'll just scroll down. There's a little calculus section, and there's 3 buttons. There's the log button for the common logarithm with the implied base of 10, so you won't see a base written there, which means it's 10. There's also a natural log button. Remember, the natural log is always base e, so you won't see that written either. And then you're going to see another common log, but with a base, it'll call it a. That means we can make the base whatever other natural number we want. Okay, so for common log with any base other than 10, then we're going to use that button. Okay, so let me just show you. Again, I'm going to go into my functions, scroll down to this calculus section. What, did I scroll too far? No. Yep, I did. There we go. So we have our common log button, and then we have our natural log button, and then we have our common log with a base of whatever I want it to be button. So in the first one, if I wanted to evaluate the log of 50, it shows me it's approximately 1.699. I'll just call it about 1.7. So let's just say this is about 1.7. Natural log of 20, I can put that in here, about 2.9957. That's pretty close to 3. Now remember, this one is asking for e to what power is going to make 20. That one would be a little bit harder to approximate even without the calculator. Like the other one, I knew it was going to be a decimal between 1 and 2. This would be a little bit tougher because e is that irrational number, but definitely going to have to be some decimal approximation to raise the irrational number to a power to get an exact 20. Okay, and then on this last one, so again, this one I can sort of ballpark. So this one is saying 3 to some power is going to make 40. We're looking for that power, right? Now I know that 3 to the third power is 27, and I know that 3 to the fourth power is going to make 81, and because 40 is right in between 27 and 81, I know the decimal I'm looking for has to be between 3 and 4. So I know it's a decimal between 3 and 4. Again, later when I'm solving, that's helpful information. That's probably going to be enough information, but for this purposes of this lesson, if you wanted to evaluate this, you'd use that third button where you can change the base to a base of, okay, let's get the cursor in there. There you go. Make the base a 3, and then log base 3 of 40 is what we're trying to approximate. So there it is, about 3.36-ish. So approximately 3.36-ish. So there you go. You got 3 log buttons in your calculator that you can use to approximate. And in fact, all of the log expressions that I worked through with you here, all of those could be evaluated with the calculator. It's just really something that you shouldn't be using if your logarithm has an exact value, because we're just looking for exponents, and a lot of these exponents you should be familiar with. But if you weren't sure when you were looking at the log base 2 of 0, then maybe this button would be helpful, right? Maybe you go in here and be like, is this something I can even do? Log base 2 of 0, and you would see right away that no, that's undefined. Okay, so all the work we did here, all of the evaluating work could be done with the calculator, but let's not reach for that unless we absolutely have to. Where we're going to go next is kind of generalize. If I wanted to connect logarithms with exponents, so in log form, we have an expression like the log base b of a, and it's equal to some exponent. Let's just call it x, okay? So the log base b of a equal to x. So what we just saw is if we took something like the log base 8 of 64 and evaluated that we got to 2, right? That is because it's the power that connects that base with that argument. So in other words, I could say 8 to the power of 2 is equal to 64, right? Well, I can take any general log form and rewrite it in an exponential form using that same connection. So even though b and a and x are just general values, there are some generic values, I can say that if the log base b of a is equal to x, then b to the x power is equal to a. So I can rewrite an equation in log form into an equivalent exponential form and vice versa. If I have an equation in exponential form, I can rewrite it in an equivalent log form. And the reason we want to be able to do this, well, there are lots of reasons, but one, it helps us in graphing log functions, but it also helps us evaluate. So for solving exponential equations, right, a log helps us find that exponent that we're looking for. Now, we're not going to do a lot of that here. The purposes of what we're doing is really just to look at the log functions, but that's the reason why some of these things happen, okay? So when we're rewriting, the important thing to remember is that the base of the log will be the base in the exponential form. So the base here is the base here. The base is the base regardless of which way you're writing this. But the exponent in the exponential is going to be the answer to the log. So remember, a log is a power. So this power here is the answer here. So the exponent in the exponential is the answer to the log, and then the other piece only has one spot to go. So the argument of the log ends up being the answer in the exponential. Okay? So let's practice just rewriting, not doing any evaluating. Right? It's not an expression to evaluate, just an equation to rewrite. Now I think going this direction is easy because I know the connection between these numbers. But again, if I wanted to rewrite the log base 2 of 32 equal to 5, it would become 2 to the 5th power equals 32. So my base is my base, and then the exponent here was the answer here. So 5 is the power that connects the base of 2 with the argument of 32. Okay? Now if it's a little more generic, then you got to remember, again, the base is the base, and the exponent here was the answer here. So if the log base x of y is equal to z, it's because x to the z power is equal to y. Okay, we're going this direction. Again, not as easy as I think this would be best case scenario, again, because I can see the connection in those numbers. Here, gotta remember, if you're going to rewrite this in log form, it's the log base 12, because that's the base of my exponential, of 144 equal to my exponent, my power 2. My log is a power, so 2 is the power that connects the base of 12 with the argument of 144. Okay? And then generically here, if a to the x power is equal to c, we can say the log base a of c is equal to that power of x. Okay? So that rewriting, again, is key to solving exponential and log equations, actually, and it's helpful when we look at log functions. So a log function is going to be of the form f of x equal to the log, let's just call it base b of x. So it's a log function, again, contains a log. The base b being almost any number, and I kind of, was a little informal when I was evaluating the logs on the other side, where I said the common log can be whatever number we want. It's not exactly true. The base of our log has the same restrictions as the base of the exponential. When we were graphing the exponentials, we said, well, the base can't be 0, can't be 1, because 0 or 1 to any power produces the same 0 or 1, a constant function, not an exponential. And we also didn't want our base to be negative. The negative, if we see that with our base, is a transformation. So just like with the exponential, we want our base to be bigger than 0. so that it's positive, and any positive is fine except for 1, so base can't be 1. Same rules that apply to exponentials should make sense apply here because the base of the log is the base of the exponential. Now, if we go to graph this, this is where it gets a little bit strange. When I'm looking for y equal to the log base 2 of x, inputting x as the argument is weird because we're not used to finding that component or inputting that component. So if I was going to graph a log function, I would rewrite it in the form that I'm a little bit more familiar with, which is the exponential form. If I was to rewrite y equals the log base 2 of x, it would be 2 to the y power equals x. Remember, the answer to my log is the exponent in my exponential. And now this is a form I'm familiar with. We were just graphing these in our previous topic. Except when we graphed the exponential, the input was the exponent. Here, the output is our exponent. So I'm going to pick my exponents, but they are my outputs. So I'm going to put -2, -1, 0, 1, and 2 here to get a good idea of what's going to happen. But those outputs are the exponent in this thing. So 2 to the negative second, remember that's 1 over 2 to the positive second, so that's 1/4. 2 to the negative first would be a half. 2 to the 0, or anything to the 0, is 1. 2 to the first is 2, and 2 squared is 4. Same thing we were doing before, but those inputs and outputs are switched. So when I go to graph this, what I'm going to see is at 1/4, my graph is down here at -2. At 1/2, I'm up a little higher at -1. At 1, I'm at 0. And then 2, 1, I have a point, and 4, 2, I have a point. And similar behavior to our exponential, but what's going to happen is as our y's approach negative infinity, so as our y's approach negative infinity, our fractions are going to approach 0. Those are our x values. So as y approaches negative infinity, x approaches 0. And so we're going to be approaching the axis this way. And so instead of a horizontal asymptote at 0, we see a vertical asymptote at 0. And let's pretend that this was actually... Let me just back up because that looks so bad. I drew my thing, the graph doing this, which is not what I want it to do. I want it to get closer and closer to that axis. So like this, but it's not going to go through. Those fractions are going to get closer to 0. So a vertical asymptote there. And then we're going to see them grow this direction. And that is what logarithmic growth looks like. So just like we have exponential growth, now the exponential growth grows definitely faster than this, but this is what log growth looks like, okay? So this is logarithmic growth. This next one is what we're going to call logarithmic decay. So just like this base bigger than 1 makes exponential growth, it makes log growth here. This base between 0 and 1 is just like a base between 0 and 1 with our exponential. It shows decay. It's a decreasing situation instead of an increasing situation. It's just the rate at which we increase and decrease is different, right? Clearly it's different. Okay, so here again, in exponential form, this would be 1/2 to the power of y equal to x. So my inputs now are what the outputs were before. So my exponents now are my outputs. I'm going to pick those exponents, plug them in. So 1/2 to the negative second is 2 over 1 to the positive second, which is going to be 4. And then this one's going to be 2, and this anything to the power of 0 is 1. 1/2 to the first is a half. 1/2 squared makes a fourth. So again, we're going to see a decreasing situation instead I should have changed colors for this. Let me just do it again. Bear with me. So sorry. Worth it on the graph. Okay, so the table flipped here. This was a 4, 2, this was 1, and then 1/2 and 1/4. So at 1/4 now my graph is up to positive 2, and then at 1/2 I'm at positive 1, and then 1, 0, same point there. 2 I'm down to -1, and then 4 I'm down to -2. So we're going to be approaching the axis this way, and we're going to be decreasing as we go this direction. So this was our log with a base of 1/2 of x, and this was y equals the log with a base of 2 of x. Okay, same basic behaviors here, just one increasing at the same rate that the other is decreasing, but a lot of characteristics that they have in common, like the domain for each of these. The domain this time is here. It's our x values either approaching negative infinity or positive infinity. No, sorry. Yeah, I said that. I think I said that backwards. But the x values here and this side are going to be capped. See how we have the horizontal, gosh, my wording is all backwards. I'm thinking about my exponentials at the same time I'm thinking about my logs, which maybe you're doing the same thing. If I'm reading this domain, let's just read the graph, okay? Those x values approaching that y-axis, they're going to get closer and closer to 0, but they can't get there. So our domain is going to approach 0, and then it's going to go, all those graphs go right forever, so it's going to go forever toward infinity, but we can't get to 0. And that was what happened with the y values of the exponential function. Okay, well, the range here, well, these graphs are going to go down forever. They're also going to go up forever. So we have this infinite range, and that's what we saw as the domain for the exponentials. Now, the exponentials all cross the y-axis at 1. These are going to cross the x-axis at 1. So we have an x-intercept at 1, 0, but no y-intercept, the reverse of what we saw on the others. And again, instead of a horizontal asymptote at the x-axis, we see a vertical asymptote at the y-axis. So vertical asymptote at the y-axis, which is where x is equal to 0. Now, the only difference between the two graphs and in general what happens with our log functions is, again, when the base is something bigger than 1, we have a logarithmic growth situation, an increasing graph. And when it's something between 0 and 1, we have logarithmic decay. We see those decreasing graphs. Again, these are characteristics that apply to the parent form of our log functions, okay, because obviously transformation rules do apply. So in the same way, I could take any of my other parent functions and shift them left or right by adding to my input, shift them up and down by adding to my outputs, reflect them over the xy axis, vertically and horizontally stretch and compress, all of those things that still apply. So if you start shifting around, then you could affect your domain or range. But in parent form, these characteristics always apply. So in the same way, you have the exponential growth picture in your head. You want to sort of plug these in there. Try to commit some of this to memory so that when you go to calculus and you're presented with a log function, you know the basic behavior of that function. Okay. Now, if you connect it, again, I was trying to sort of do this as I was going here, but let's just look at the same time at these two functions. So this is exactly what our exponential picture looked like, right? Last topic, where we have the exponential growth. In this case, it's 4 to the x, and we see the horizontal asymptote at 0, right? We see the y-intercept here happening at 1, and all the opposites happening for the log base 4 of x. So when we rewrite this, this would be like 4 to the y power equal to x. Everything was flip-flopped. The x's and y's are switched over here. This would be like y equals 4 to the x, right? Inputs and outputs are switched. And so instead of crossing the y at 1, we cross the x at 1. Instead of the horizontal at the x-axis, we had the vertical at the y-axis, right? And all the inputs and outputs were switched in our tables. And we see some symmetry in this graph about the origin, the parent linear function here. And so what we see, hopefully, is something that's ringing a bell. If everything input and output is switched, all the inputs and outputs are switched, the domain and the range are switched, right? This point here at 0, 1, the opposite here at 1, 0, everything is switched. These are what we call inverse functions, and I'm hoping that word was already jumping out at you. That is exactly the characteristic or the characteristics that we see, the connections we see between a function and its inverse. So if 4 to the x and log base 4 of x are inverses, but we just said we take something that's in log form and put it in an equivalent exponential, how can exponentials and logs be equivalent, meaning basically the same, and also inverses? That's kind of mind-blowing to me. Let me try to show you. So exponential functions and log functions are in fact inverses of one another, but there are also equivalent versions. So if I was to look at, which direction do I want to go here? Let's say I was looking at y equals b to the x power. If I said to rewrite that in an equivalent log form, it would become the log base b of y equal to x. Okay, so that is the equivalent form, right? That is the equivalent form. But if I was to write the equation for the inverse, then the inputs and the outputs would switch. So if I wanted the inverse of this function, I would switch the input and the output. And so what we would be looking at is the log base b of x equal to y. So from this one, we're looking at an equivalent form. The exponent here, the answer to the log. But when I switch the inputs and the outputs to get to this form, I have the inverse. So those are equal. The first two are equal, but the second two are inverses. And which means, okay, if these two are equal, but these two are inverses, it means, oops, going too far with my undo. It means that these two are inverses as well. I hope that makes sense, because in my head it does, right? So we have an equivalent form where we rewrite, but then when we switch the inputs and the outputs, we know we're looking at the inverse, okay? So basically, in general, when you go to switch the inputs and outputs of your log form, we are looking at the same base here, right? X in the same, well, it looks like b to the x here, it looks like b to the x here. That's the sort of part you want to connect in terms of inverses. So if you're looking at a function y equals b to the x, its inverse, which we'll call f inverse of x, will be the log base b of x, okay, always. So if you are looking at, let's say, y equals 5 to the x, and I said, what's the inverse? It would be y equals the log base 5 of x. Or if I said, if we're looking at y equals, let's say, 1/10 to the x power, then its inverse would be y equals the log with a base of 1/10 of x, where this is sort of the picture we would see graphically for each of those exponential functions and the inverse of each of those exponential functions. Just be really careful, because these two are opposites. Okay, if I switch the inputs and outputs, then I have something equivalent. Alright, so if I said to write an equivalent form of this, it would be the log base of 1/10 of y equal to x. So these are equal here, but inverse to what we see here. Alright, so inverses and equals at the same time, but hopefully those connections are all feeling familiar. Okay, so the big takeaway, most of the recap here with the logs is just to make sure that we had a solid understanding of what a logarithm is, but here's the big takeaway, okay? When we get to calculus, we want to understand the basic behavior of functions. So a log function, being the inverse of an exponential, does all the opposites of what the exponential does. Instead of the y-intercept at 1, x-intercept at 1. Instead of an infinite domain and a range from 0 to infinity, the opposite here. We have a domain from 0 to infinity and an infinite range. Instead of a horizontal asymptote at 0, it's a vertical at 0, okay? So if we can commit some of this to memory, again, it just makes our lives a little bit easier as we go to calculus and do some further analyzations with functions. Alright, so I'm hoping you're good and you got enough to get going on that homework assignment, but as always, if you need some extra help, then reach out. Till next time, take care.